and good afternoon. I'm going to present our research on polar organic light emitting diodes and how we can use them as metal-insulator-semiconductor devices for parameter extraction. When we aim to do parameter analysis of organic electronic materials, a very good approach is to simplify the layer stack. And for OLEDs, we can actually use the bilayer configuration, just consisting of a hole transport layer and an electron transport layer. And we will use the very prototypical materials, small molecules, alpha-NPD or TPD as hole transport material, and ALQ3 as the electron transport material. If you look in the literature, this is actually very old, and this has been done for about 20 years now. So you should think that there is a lot of knowledge already, and Wolfgang Brütting and others have started to investigate these kind of devices using impedance spectroscopy and also capacitance voltage experiments. In a standard or normal capacitance voltage experiment, you would observe a curve like this. So under reverse bias, you observe the geometric capacitance, the diode is blocking, there are no charges inside, and the geometric capacitance of the full device is what you will measure. If you increase the voltage, at some point charges are being injected, the capacitance increases, and when the bipolar injection sets in around the built-in voltage, you will find this peak of the capacitance. Interestingly, in these kind of devices, what was very often or most of the times observed is a shape like this. So what we see is that the capacitance increases far below the built-in voltage. So this threshold voltage can even be at negative voltages. And if we investigate this capacitance plateau, this corresponds to the capacitance of the ALQ3 layer. So we see that in this voltage regime, there are already holes in the alpha-NPD, while the ALQ is still insulating. And when the thickness of the ALQ3 layer is varied, we find this linear dependence of this transition voltage with the thickness of the ALQ, while it's not depending on the thickness of the alpha-NPD. There's even a formula for this linear behavior, and the explanation for this behavior is that ALQ3 forms a polar material, a polar film. So during the deposition, during the film formation, the molecular dipole moments of ALQ orient non-randomly, so we end up with a film that has a macroscopic polarization. And in this very simple picture, we can describe it as two sheet densities on both sides of the ALQ3 film. So the main difference, if we compare it with a non-polar device, in a non-polar device, we would have a built-in field at 0 volts, which prevents both holes and electrons from being injected. However, in this polar configuration, we have this like compensating field due to the sheet densities, which reverses the field in the hole transport layer and leads to an injection of holes already at 0 bias. So what we find is we have an accumulation of holes at this internal interface. And when we saw this, we thought this actually looks like a metal-insulator-semiconductor device. So the ALQ3 is an insulator, and the hole transport layer, the alpha-NPD, is the semiconductor. So perhaps we can also use this for parameter extraction. There is a technique called MIS-CELIV, where CELIV stands for charge extraction by linearly increasing voltage, which is used to determine the mobility in MIS devices. So a MIS device would have such a configuration. We apply some bias, which leads also to injection of, in this case, holes into this layer. Again, we have this accumulation. And at this point, we start to extract the holes using a linear voltage ramp. So we extract all the holes back to the contact. And this will lead to an overshoot in our current signal, which is related to the mobility. So this is well-known technique to determine the mobility in organic semiconductors. And we wondered if we can apply it also in our bilayer devices. So we did some drift diffusion simulation. It turns out that it really behaves the same way. So if you look at the band diagram, so these were the schematics, these are the simulated band diagrams. And they really look like we have assumed them. And especially if we look at the charge densities, we find that the holes really accumulate at this internal interface. This means that the analytical model for the MIS-CELIV experiment can be employed. So in the MIS-CELIV, there is some analytic framework to estimate the mobility from either the peak position or from this initial slope. And this is valid in case the holes are all accumulated on one side. So this can be applied, and this is actually the literature for the MIS-CELIV theory. And we could analyze this transit time using this specific formula. This is what we got in our devices. So it looks very reasonable. And under the so-called small charge limit, we get the mobility of holes in alpha-NPD to be around 10 to the minus 4 centimeters square per volt second, which is also in very good agreement with literature. So it's again a confirmation that we can apply this method for these devices. And now we actually went a step further. We looked at the temperature dependence. This is again the same measurement at different temperatures. And if we again evaluate the mobility, we find a very nice Arrhenius behavior. So this is a thermally activated quantity, and the activation energy is around 0.25 electron volts. So as I said, what we are doing is we extract these holes outside of the layers. So we would assume that the activation energy we measure here is really the thermal activation of the hole mobility. And there is another experiment that we even did before that. It's the capacitance frequency versus temperature. And also here we see a very clear temperature activation. Like in the capacitance voltage, we see these two plateaus of the capacitance, so the geometric value and the capacitance of the ALQ3 film alone. And we see this transition between the two plateaus. We see this relaxation frequency shifting or being very nicely thermally activated. In a very simple equivalent circuit model, this can be already explained. So if we look at these two layers as two RC elements, if we increase the conductivity of the whole transport layer, or if we decrease the resistivity versus temperature, this directly introduces this shift of the relaxation frequency. And in this case, the question is this conductivity of the whole transport layer. It depends not only on the mobility activation, but also on the injection barrier. So what we would assume is that actually we obtain something like a sum of these two energies. And again, we wanted to find out if these assumptions are true. So we did simulations, and we did many simulations. So we varied both the injection barrier and the mobility activation. For the CELIV case, where we assumed that we would determine only the mobility activation, we find that this is true for the lower injection barrier. So if we have very good contacts, this works well. So we can really determine the mobility thermal activation with this experiment. We also see, obviously, there are some deviations for larger injection barriers. And if we look at the capacitance frequency versus temperature, we see that the mobility activation does not introduce an additional error, but we also find there is some deviation from the expected values. So the dotted lines would be what we expect in case we observe the sum of these two energies. And, well, the points are what we really get. So there is some error, but if we combine the two experiments, we think it's already much better a much better estimate of these parameters. Finally, I'd like to show one slide on how this polarity really affects the device performance. So it's not only good for parameter analysis, but it's even beneficial for the performance of the devices. This is a simulation of just the current voltage curve with an unpolar device, and the green line corresponds to the ALQ3 case. So we have a polar layer, and we see there's a better injection, there's a higher current, which is because we have this sheet density on the electron injecting side, which actually improves the injection. And on the other hand, if we would think of an inverted polar material, and there are some molecules that show this behavior, we would obtain a very bad IV curve. So actually, again, the sheet density with the wrong polarity will lead to like an increased injection barrier for the electrons. So with this, I'd like to summarize. We saw that these polar OLEDs, polar bilayer OLEDs, act like MIS devices in this specific voltage regime, and this can be exploited for parameter analysis. And perhaps one advantage to the conventional MIS devices is that ALQ3 is very easy to process and to fabricate, while insulators might be more tricky to process. The work I presented was performed in the CARDIN project, which is a joint project with University of Augsburg and Institute of Computational Physics here in Winterthur, and which is funded by the German and the Swiss Research Foundation. Thank you for your attention.